Closures are an interesting feature of most modern programming languages. Essentially, a closure is a function that will retain state for later invocation. So we're going to actually use higher order functions here. In other words, we're going to create a function and store it in a variable and invoke that variable at a later time. But instead of passing everything we need at that time when we invoke it, we can cache some information into that function object ahead of time, and then when we invoke it, that data will still be there. I'm going to create a function called multiplier. And as you can see with multiplier, we are going to pass in a single variable called n, so one value. Then we are going to return a function that will actually do the multiplication. Again, we are using a higher order function here because one of the criteria of a higher order function is either A, it has to be a function that accepts another function as a parameter, or it has to return a function as its result. So we are going to return a lambda because a lambda is an anonymous function. And this lambda will accept a single parameter that will multiply that parameter by n. So let's break this down a little bit. We have a function called multiplier which accepts a variable called n, or a parameter called n. You can see that n is here. This right here represents the body of the lambda function that will be executed at a later time. And as you can see, the input to that function is a single parameter x. So we are going to cache n for later use. And then when we invoke this lambda, we will pass in the x that will be multiplied by n. Let's take a look at how it actually works. I'm going to create a variable called doubler, and I'll set that equal to multiplier with an I, and I'll pass it a 2. So this 2 will now represent the n. So the result of this call to multiplier is not the actual multiplication. It is a function that will be invoked later that will multiply whatever we pass in by 2. So I'll run that. So as you can see here, if I print doubler, it's not actually going to be a double value. It's going to say it's a function. It is a lambda function. So how do I invoke this? I could say print doubler, and let's say we wanted to double 5. So now what's going to happen is this 5 is going to get passed in for this value x in the lambda. The 2 has been cached. Okay, notice here we passed in the 2 ages ago. We don't retain that in a variable anywhere out here. Okay, so it is being retained in the function object itself. And as you can see, we get the value 10 as a result. What happens if we print doubler instead of 5? We'll do 7. So it should double 7 and give us a 14. We can create yet another closure by calling this one tripler, which we will also use multiplier. And this time we'll pass 3 for the n. And now if I wanted to triple something, I could say print tripler, and we will use 5 once again. It should give us a 15, but we can also pass it a 7, which should hopefully give us a 21. So as you can see, this tripler function is being held in memory. 3 is being retained for n for later use. And anytime we call tripler now, whatever we pass, it will triple. Now, an interesting feature of Python is because we're not exactly type safe, in other words, we're not forcing this to be an integer, What happens if we passed 5.5 instead? We get 16.5. What happens if we pass something else, like the letter A? We get 3 A's. So whatever the operator is used for that type, like in this case the multiplier, when it's numbers, it will multiply by 3, because that's what we assign tripler to be. The n will be a 3. But if we pass it a string, anytime you take a string and multiply it by a whole number, it just repeats that string that number of times. So it essentially tripled our A. We don't actually have to retain that closure in a temporary variable. We could actually call it inline. We could say multiplier, and then let's say we wanted to use 6 as the multiplier. So we know this is going to return that lambda. So we will then have a function stored in a, you can call it a temporary variable. It's inline right now, but that multiplier 6 is going to return a function. How do you invoke a function? By passing it a parameter. So this is going to create the closure, the multiplier 6, where n is going to be 6, and then we're going to invoke that closure by passing it a 4. So it's going to be 6 times 4, and hopefully we do get a 24 out of this. So this becomes a really interesting syntax, because it's not something you see commonly, where you have a set of parentheses immediately following another set of parentheses. So you just have to remember, multiplier is returning a function, and when you invoke a function, you have to pass it the parentheses. Even if we pass nothing to the function, let's say we had a lambda that didn't have to accept a value, then this would just be an empty set of parentheses, but you would still need the parentheses there. Another demonstration of closures will also introduce something you may or may not already know, which is the ability to embed a formal function within another function. So I'm going to create this function called square me later. And square me later is essentially, as you could guess by the name, going to take a value and square that value later. Okay, so we are going to retain the value passed inside this function. We're going to say value is equal to x. And then I'm going to define yet another function in here called square me. So this is the one that's actually going to do the work. And it's going to return value squared. Because of the way scoping works in Python, when I declare a variable at this level, anything at the same indentation level or inside can utilize that variable that's declared here, even if it's within another function. This is traditionally how closures may work in other languages, where you may not even pass the value in to this function. You're just using it based on scoping. And then, because we are creating a closure, we're not going to return the squared value. We're going to return square me, which is essentially a reference to this function here. So then I can create, I'll call it SML for square me later, and I'll set that equal to square me later. I'll pass it a 10. So now if I print SML, we should see that it is in fact a function. Okay, it's defined in square me later square me. That's the name of the function. You can see how it is scoping it. So we have the outer function name, inner function name. And all I have to do to invoke it is say SML like it's a function call. And now it'll print the value 100. So we created the closure here with the square me later call. We pass it the 10. It retains that 10 inside the value variable. We define an internal function here called square me, which utilizes value. But since we are not executing square me yet, this value must stick around inside of this object's cache for as long as we keep this SML function variable alive. So at any time I want to run it from here on out, it is going to retain that value of 10 until such time as we delete SML or the variable falls out of scope. Because I defined it here at the leftmost indentation, the scope is essentially the life of this module, so it's not going to be falling out of scope anytime soon. It's kind of a funny statement, but some critics of closures have said in the past that it's a solution waiting for a problem. And that's a little harsh because actually this can be useful, as you can see up at the top where we have a generic multiplier and then we set it to a specific multiplier value, one of the factors, that we can call anytime later on. Let's say we have to multiply something by pi a lot in our program. Well, we could set up this closure to already have calculated pi and holding pi in memory, so anytime we needed a multiple of pi, we would just execute that closure without having to pass two separate variables. Again, there's not a lot that closures do for us that we can't do with traditional programming techniques, although as you'll see, because we're going to keep building on these concepts, you will see where closures can come in handy later on with other concepts, such as currying functions.